Can everyone hear me? If somebody hear me, can you just say yes in the chat room? There's a chat room somewhere. Hi, morning.
Testing.
Hey. Testing. Okay, and you will use 2 mics. If I talk like that, can the Zoom people hear me? Can you hear me on the Zoom people? Someone say yes if you can hear me. Is it very clear? Okay, thanks. That will be a lot better, so I don't need to put my mouth facing the mic. Okay, everybody okay? So good. We are all set to go. This technical thing. Okay, good. Thanks for the Zoom people for the reply. I see if anyone shouldn't be anyone in the waiting room some more. Okay, so yeah, I think everybody is still sleeping, but anyway, we have the web lecture anyway. So just in case somebody don't know, all the web lectures are recorded and can view in Luminous. Okay, Luminous have all our webcasts. So somebody don't know because we too much focus on cosmology. Okay, but Luminous actually have all our webcasts. So if you miss out anything or the Zoom have some problem or something like that, please feel free to go and watch it in Luminous. Okay. So I will leave it here. You guys stay quiet here, and I will start the lecture. Today's lecture will be a bit more easy, okay? Because what happened is yesterday we have quite a very difficult lecture, and today we have a quite easy lecture. It's a big step down, okay? So today we talk about trees. I think some of you may learn in 1231 already, okay? So today may be a lot of overlap. So bear with me if you feel it's a bit like not very new, okay? But before that, let's set up with some more true problem in the world, okay? For example, you see that real world, if you want to put some data into a collection, usually you just don't put an integer. You see when we are doing the tutorial or the class example or assignment, we just put an integer or put a simple food record, okay? But in real life, seldom do that. A lot of time we actually have one record. For example, if it's not Pokemon database, okay? It was Pokemon database, okay? For example, let's say if I want to do a flight scheduling. So what I do is I actually one record of flights can have a lot of information. You can have the arrival time, you can have the departure time, you can have a flight number, you can have where from, where to, how many times, how many hours, how many passengers, you have a lot. But usually you try to arrange them according to one of their fields. For example, here, actually, I want to arrange all the flights according to the arrival time or departure time. Let's say departure time is actually flight taking off time. Okay, depends on what is your use. Okay, if I want to schedule the runway, okay, then you record both arrival time and departure time. So let's just say gate close protocol. Okay, we just record all the departure time. And that means the departure time is actually your key. Okay, you want to arrange. Let's say I want to arrange every plane with a key that is according to departure time. Then I actually have a sorted list of all the planes according to departure time. Okay, and what happened is the second point is more important is because usually this type of data set are dynamically allocated. What does that mean? You can add new things. You can remove something, or you can modify something. Let's say this flight originally is scheduled to depart on 8 a.m., but actually changed to, let's say, delay. It changed to 9 a.m. Okay, the entry and arrangement and the order can be changed. Otherwise, it's very easy. I just need to do a sorting algorithm, right? I just need to sort them. I just need to get all my data, all my flight today. Okay, I'm happy today the flight won't change, then I just sort them. But usually, I will say 99% of the problem will be dynamically changing. Let's say even our class students, people come in, people drop out, people want to withdraw, people want to wait until next semester. So even in the semester, or even at the end of the semester, the student cohort of one class is always changing. Let's say the final exam, some people submit an MC and need to exit from this guy and take it again and this and that. There's a lot of things happening, okay? So usually our data set is dynamic. And with this dynamic data set, we want to query or ask a lot of questions. The simple question is, I think we had it before, like, is the data in the array, in the data set exists, okay? Is it existing? Or the other information we actually want to ask more is, what is the next flight after 8 p.m.? Let's say I really, really want to go away, okay? I don't care. I just want to catch the next flight after 8 a.m. But you know, there's a lot of flights. So what is the next flight? Or what is the previous flight? Or let's say if I want to say, I want to schedule the plane to land on 8 a.m. But I need to occupy the runway for 20 minutes, okay? Let's say the flight taking off or landing is 20 minutes. Then I want to see the flight before 8 a.m. and after 8 a.m. Do we have a 20 minutes window? Right? We have a lot of queries that we need to know even the neighbors. We call it the successor or the predecessors, okay? So we actually need to find the one before or after of a certain time, even though the time I asked, let's say 8 a.m. just now, I say, may not be even in the list. So we want to do this kind of queries. And this is what we try to set up, okay? This is what we call a dictionary ADT. This is ADT as in, if you went through the tutorial, you also know the set ADT, which means I want to specify the functionality first, and I don't care about the implementation, okay? So what I need is, of course, I want to insert an item. So the key is actually depending on how you arrange the items. For example, if it's in the last example, I want to insert the key as my flight departure time. And my record is my value, which means the whole flight information. Which flight is it, what is the flight number, where this to, or whatever, okay? And of course, I want to search. This search is actually our exists, okay? Which means, do we have a flight with that departure time? Okay, let's say I want to search for 8 a.m. Is there a flight on that spot? And these two are the extra one. I want to find what is the next and before the time, okay? One thing you notice that it could be the time is not even in the database. Okay, let's say I have flight scheduled 8 a.m., 9 a.m., 10 a.m. already. But actually I want to ask, is there a flight after 8:30? In which 8:30 is not in the database, okay? No flights on 8:30, okay? So there is the successor and predecessor, okay? And of course, you can remove a flight, or you can Okay, this exists. Okay, this search is actually returning the whole record. Okay, so the search and it contains a bit different. So actually, sorry, I made a mistake. This actually the real exists. Exists just answer you yes or no. Is right there. But this one search is with the time. I actually search out what is the flight information on the time slot. Okay. Well, we can try. I think we also try this in our lab session this time. Let's say we want to implement a set. Maybe you can just use arrays or linked lists. Okay. But if you use array, I can sort it. I think in my lab section, a lot of students actually raise the ideas of if we want to implement a set, we sort it. But you know set, you don't need to sort, okay? But this one is more intuitive to sort. So if you sort it, when you add a new entry, you need an ON. You need log n to search because you can use bisection method. But after you search a position, you want to squeeze yourself inside the array, you need to move everybody after your array to be moved one right direction, okay? So, and then search can be binary because it's sorted, so it can be log n. However, if you use the linked list, you always also need ON to add, and there's no binary search, so too bad. Linked list, you cannot do that, okay? Then, I think that's why we use tree, right? Tree is, you can actually just arrange every item in a tree, and some mod is called, but there's many types of tree. Okay, when you talk tree, you say, oh, this is the one we want, but actually not. We actually have first the tree. Does it always you need 2 children? Actually, there's no constraint. If you talk about the general idea of trees, every node can have more than 1 children. Okay, so we're talking about binary tree. Okay, about these 2 are not binary tree, it's just 2. Binary tree means each tree I have 2 children, okay? And the most top of the node, we call it the roots. And whenever each node you have a parent and child, okay, it's a bit like our normal family tree concept. So this is a parent and you have 2 children. And between in the same level, have the same parent, we call them siblings. Okay, so it's like normal. And if you have a node that does not have any children, we call it a leaf. Okay, and somehow it's like a normal tree, but you grow upside down. Okay, so it's a Batman or it's a Spider-Man binary tree. Okay, so the root is actually on top. Okay, our tree is quite anti-gravity. Okay, so, and then you have the left link or right link, or you call it left branch or right branch. And there's a left child of the roots, and there's a right child of the roots. Okay, and if you talk about a collection, you actually have a left subtree and the right subtree. Okay, actually I generalize the left is actually another tree, right? It's a recursive definition, and the right subtree. So talking about recursive definition, if you want to talk formally, a binary tree is either empty or a node that point to 1 or 2. So you can have empty or 1 or 2, actually 0, 1 or 2, okay? 0, 1 or 2 trees, okay? So it's a node, then you have right, left, okay? So if you want to talk about C++ code, I can actually implement a record like that. So I have a point, I have my item that I'm storing in a node, and I have left and right, okay? So pointing to a left tree node or right tree node. And your tree node, actually, you can initialize that the left and right at the beginning. You don't point to anyone, right? Because you just create a node or tree, and then you want to store the item, and the height of that is 0. We'll talk about the height of each node, okay? Each node have a height. And you actually, it's like in the linked list, right? Linked list, you have linked list node and linked list. And then you have actually binary tree node, and you have actually a binary search tree, okay? And this the tree is like the linked list, you have this the engine of the train, right? So you actually, this is a tree node, which is the roots, and you actually start to set the roots to be null, which means when you start creating a binary tree, you have no nodes there. Okay, so we were talking about binary tree, but we didn't have this binary search tree, okay? Actually, binary tree, you just need to constrain the shape into 2 for each parent, right? But binary search tree has this property is all the key on the left are smaller than your key. For example, you can see here 41. All the 3 nodes on the left of the tree actually smaller than 41. And all the right is bigger than 41. And it's recursively defined for every node. For example, 65, everything on the left of 65, which does not include the parents, okay? Over here is not 65 children. All the left children of 65 is smaller than 65, and all the right children of 65 is bigger than 65. Okay, so it's a binary search tree. And let's do some basic operation, okay? For a tree, we actually define the height for every node, okay? So the definition is quite simple. If the nodes is a leaf, then the height is 0. For example, you can see 11, 32, 72, 99, their height is 0, okay? And if you are not a leaf, that means you have some children, so you actually take the height of the children plus 1. Okay, for example, you can see 20, okay? So for example, this is 29. 29 have no children, but you actually have a height 0, so 29's height is 1. So 91 is 1, and 65, you have a height 0 and height 1 of your 2 children, right? So V left is equal to 0 for 65, and V right is equal to the height is 1. So your maximum 0 and 1 become 1, and that's why the height of 65 is 2, and so on, okay? And lastly, the height of the root is 3. And the height of the whole tree is the height of the root. So that's the height of the tree, okay? And we can compute the height of the tree, okay? So if left is not equal to null, then we actually take the left height. If right not equal to null, you actually take the right height. And then your computation is the max of the left and the right plus 1, okay? But of course, there will be a, what if left and right are null? Then you just set it to be -1 for simplicity. Okay, that is a convenient hack. If you see the last node over here, for simplicity, we assume an empty tree is -1. Because if you have a node that is not empty, one single node is height 0. So if no node, then it's like empty one. So that's why we set it here, this one, okay? So we actually assume the left height, if the left subtree is null, is -1. That makes everything easier. Okay. So how do you search the maximum item in the tree? Just go right, okay? Because your right side of your children, the right child of your children are actually the bigger one. So I just need to start from the root and go right, okay? Go right, whatever it is. Go as right as I can. So search max is you start from the roots, and while you still have a right, you actually go to the right until your current right is null. Not your current is null, okay? There's a difference between your current is null and right is null. So you actually reach a node that current is not null, but it has no more right child. And that's the answer. Okay, it's very simple. You just search for the maximum in the tree like that. Okay, so for a tree, you just, for example, let's say if you follow that, 41 go to 65, go to 91, and 91, the right child is null, and that's why you stop at 91, and 91 is the largest. Okay, so you start at 41, and you go to 65, 91, 99. Okay, so 99 is the largest of all the nodes. Okay, how about search for minimum? It's easy, right? Easy. Minimum, you just go left, okay? Go all the way to left. So you just change the code here, while current is equal to current left, okay? So you just go left as a minimum. How about I search for a particular key? For example, I want to search is 25 is in a tree. Should I go left or right? It depends on the current node you are at, right? for one node, let's say 41, I actually knows all the numbers smaller than 41 is on the left. All the numbers that is larger than 41 is on the right. So if I'm now searching for 25, should I go left or right? Left, right? Because all the numbers smaller than 41 is that. That's why I go left. And I just follow this rule. If it's smaller than the current node, I go left. Otherwise, I go right. So this binary search exists. So I starting from the roots, and when my current is still not null, if the current item is already my item, because I search, it's a possibility that in the middle of searching I find my item, right? Then I return the item. I return true. Otherwise, if my thing I want to search is bigger than the current item, I go right. Right? Current is equal to current right. I go right. Otherwise, I go left. And I just keep going down the tree until you return true here, which means I found the items, or I exit this loop when current is equal to null. When current is equal to null, that means I actually reached the end of my tree. I still didn't meet my item I want to search, then I actually can return false. Okay, so that is the binary search of the tree. So for example, let's see if I want to find 74. 74 is larger than 41, and go here, and larger than 65, but now smaller than 91. Bingo. Okay. So if the key is not in the tree, then actually I will go all the way out of the tree to get a null, and that's I return false. Okay. How about inserting a key? I want to insert a new node. I actually can follow the search rule, right? Because if I want to insert a 25, I want to insert on the left of 41. Because they're supposed to be, because everything smaller than 41 should be on the left, okay? So I follow the same thing. So if the current item is larger than X, I go to the left, okay? If there's some current left, the current left is actually equal to I insert the item in the current left tree. The way I do it is because then this can return a new tree. That is not current left. Okay, so this actually happened when you actually current left have this actually for later the rotation or something. Okay. Otherwise, current left is equal to new node, because that means the current left is actually was equal to null. No item. Okay, so you actually do that, and you do the same thing for the right. Okay, so this is one I purposely leave it out, and you try yourself. Okay, and then else return current. Okay, so what do you mean by else? Else, there's actually a possibility it's not larger, not smaller. That means maybe the item already in the tree. Okay, actually it's not only returning current. Maybe you need to do something. That depends on your application. That means I already have something you want to edit. Usually is an error. Okay, so that is other thing. But here I just return current for simplicity. But for example, let's say I want to insert 27. I search 27 until 29. Actually, this should be 29. Okay, I search here. I should go left. For the left is null. That's why I can directly add 27 there. Okay? Yeah. But what is the time complexity for all this operation? Exist, search, insert, whatever. Okay. If you notice that I can actually have a lot of the tree actually can have different shapes. Even you can see the two trees here have the same items, or one tree can be almost like a linked list. You can think of the right one, right? The 41 on the right, this side. If you already have n items in the list, what is the time complexity if I want to add 99 now? You have to go all the way to the end, and that means the time complexity is O(n). But how about this? I don't want to give out the answer yet, but one main, actually is the most important concept here is every operation depends on the height of the total height of the tree. Okay, and today we won't talk about how to make the tree height shorter, but that is the topic next week, okay? But just bear in mind, every operation, we're just relying on this very important quantity for the height of the tree, okay? Yeah. And you actually, even with the same data set, you can come out with different tree shapes, okay? Some tree can be, we actually call this tree very tall because the height is very large. We can call this tree very flat because the height is smaller, okay? So this is the next week's topic. And actually, what determining the shapes is actually the order of insertion. I insert things in different order, but still depending on the binary search tree property, I can actually come up with different height, okay? Yeah, so every time complexity now depending on the height of the tree. So a tree with n nodes can be having a height of On or O log n. Can it be smaller than O log n? Actually, we proved it yesterday, right? A tree with n nodes cannot have height less than log n, okay? Because that's how we store, okay? But next week, we'll talk about how do we maintain this. That means if we want to keep adding nodes, how do we maintain the tree height is log n? As in, how do we organize the tree, okay? But today we'll skip it because of the time constraint, okay? Okay, lastly, not lastly, I think it's the traversal, okay? This is called in order traversal. That means how do I print out every item in the tree? And it's not like linked list. Linked list, you only have one order, right? From the start to the beginning. But now your tree is branching. So this, we have 3 different orders, okay? This is called in order traversal. In order traversal means I will traverse recursively with the left tree first, and I'll finish all the left 3 items, and I do something about myself, okay? Because in order traversal, a lot of time you actually get the order and do something, right? Or output it to something. But here I just print it out. So I just do print out, but actually you can do something about it, okay? But that's other thing. And after I finish the left 3, process my own keynote, and I process the right 3. Okay, let's try. The in order chart, how come I don't have the, how come this is not the most updated version of my slide, sorry. You should end here. Okay. No wonder I lost all the, okay, where's my, sorry, I think, where's my Google? I should have still have slides, but just don't know why. You cannot force quit the Google Drive. Oh, yeah. But anyway, I think I store the PDF version there. Okay, let's try the PDF version. Okay. It's just that this computer didn't update the drive version. I don't know why. Maybe because so let's use the PDF version for now. Okay, so yeah, okay, so yeah, sorry, I need to use a PDF version, and yeah, that's why you see I have all the things, but I don't know why just the thing can, yeah, you see this Dropbox and Google, okay, I can get it. Google Drive, I quit. And I need to launch it again, then I can get the update. Sometimes the computer don't update the things when, okay, hopefully it updates when you open it for too long. Okay. Hopefully update already. Yeah, it's up there already. Sorry, it's just that. Okay. Okay, let's continue. Okay, so this is the in order traversal. Okay. Let's start. Okay, so actually it's a real slide. Okay, so we start by calling in order traversal from the root, right? And you can see that I actually directly enter the in order traversal of the root left. So you actually go here. Okay, and you didn't print out anything yet. And when you go this look left, you also go in here. Okay, because you keep recursing at the start of your recursion. So, and after that, you actually go to the now, okay? Because actually the left is now. So in the code, if it's now, then actually you return already, okay? So you come back here. And now you're actually at the node of 11 and you print it out. So what you print out is 11 now. And you go to the right of the 11 in which there's nothing, okay? So I think the order is you process all your left, you do your own key, and then you do anything, okay? And then you return to 20, and now 20, because all your left node has been processed, and now you do 20. And the next one, you go to 29, okay? Do you print 29 now?
No, you go left first.
Not yet. You go to the left of 29, which is here. Actually, you have to go to the left, which is now, and then you go there and return. And then you print 29, okay? So that means if there's some 29 have some left child, you need to finish that first. But this one don't, but you still need to go to the now and come back. And you go to the right child, and 32, because 32 don't have any child, you go to the left child, which is now, and come back and print 32. Okay, so you go to the left child of this 32, which is now, and you print yourself and go to the right child of this, and then you return, okay? You return, okay? You 32, you return to 29, 29, you return to 20, and 20, you return to 41 now. And 41 now, because you finish all the left item of 41, that's why you print 41. So if you notice the number here is the order we have so far, okay? And then you go to, and if you follow that, this number, you actually have this order of printing out. And you notice what is that? It's just a sorted order. Okay, but it's natural, right? Because in order I process anything on the left first, which is all smaller than me, and then I process myself, and then I process everything on the right. So it's naturally and sorted order, okay? And this in order traversal, and the time complexity is ON. ON means I actually just traverse every node one time, right? I don't need to go back. Every node I just, yeah, it's a return, but the processing, the C out is only one time. So actually it's still ON. And the thing is, what if we move this processing in other? So now the order is I recurse, I process, and I recurse. Which means I recurse my left, I do this, and then I recurse my right, right? What if I do this? I put the recursion, I put the processing on the left, then I recurse the other two. This is called the pre-order traversal, okay? And what you do is, actually, if you trace it, I do 41, but I process it first. That's why I print 41, okay? And then I print 20. And then I print 11. And then I go to left of 11, right of 11, come back, and come back to 20. And then I print this. So you can see the order of this is, whenever you visit the node, you already print it. So it's the in order traversal. And the rest is the post order, okay? The post order actually gives you this. So this one is just an exercise. If you really want to see the animation, you can actually see the visual algo. You should have this order very nicely animated, and you can actually pause and go on by yourself, okay? The other one is called level order traversal. The first level is 41. The next level is 20 and 65. And this is like that, and like that, okay? But this one, I don't give you the code. Think of what data structure should we use for that. Okay, this one actually is kind of a test whether you understand all the things before. Okay, the hint is all those ADTs, okay, maybe step queue or something, and try to think about how to actually do this level order traversal. Okay, so come back to our application, let's say airport scheduling. So the thing we want to talk about, what is the next item after X40, right? So what will we actually so-called how can we find the X30 item? But it's called successor queries, or if you want the previous one, it's the predecessor queries. So what happens is, let's say I want to find what is the next one in 41 in my list. Okay, so I can try. Let's try. Okay, I just search. Okay, if I want to search 41, I will end up with 50. Is this a successor?
Yeah.
Yes. Right. But is it always that lucky I can find that? For example, how about this? I find 33. If you follow that, it's 32. Okay, if you follow your search, you end up at 32. Because if you follow the left, smaller, right, bigger, then how? Okay, and well, but first, you can actually basically think of it. If I want to find a successor, the strategy is I search for a key in the tree. If the result of the search is larger than my key, I'm done. That is actually my result. That should be my closest one and actually larger than me because I check it is larger than me. But what if the result is not equal to, because you actually can find that key, right? You are allowed to do that. Let's see how. If the successor is in a tree, okay, let's say I want to find what is a successor of 20, okay? Which one is a successor? You have actually three choice, right? I don't know why I lost all those animation also. Okay, so never mind, just go on, okay? You're actually surrounding 20, you have a few choices. One is your left child. Will your successor in the left child? Not possible because all the left children are smaller than you. Will the successor have two choices? One is on your parents here, go over here, right? The other one is if you have a right child, will your successor on your right child, or your right subtree? If one looks, let's say 20 have a right subtree, will your successor in here, in the right subtree, or in the other side after the 41 over that side? Which one will it be? If your 20 note have the right children and also have parents, your right children will be better than you. But because your right children is still belong to your own 20 subtree, your right children will be all smaller than your parent. But provided that your parent come left, okay? So that's why if you have a right children, so you just need to find the minimum in your right subtree. Does that make sense? So all your right subtree is bigger than you. And your successor, which means your next larger than you one, will be the minimum over there. Okay? Case closed. So if I search a node which is inside the tree, or actually even not inside the tree, and I stop there, I check whether it's a right child. Okay, a right subtree. If you have a right subtree, then you actually find the minimum of the right subtree. Okay? But what if you don't have a right child? Okay? What if you don't have a right subtree? Let's say now I want to find the successor of 11. I don't have a right subtree. Who is my successor? Who is the one slightly bigger than me? Maybe by your eye, you just see here. Which one? 20, right? Yeah. Okay. How about if I want to find the successor of 22? Which one is my successor? 40. I'm sorry, 41, right? Hey, but wait, what is the rule? You know, when we talk about algorithm, we need the rules, right? By your eyes, you can see all the numbers and tell, okay? So let's put it together. Any hints you get it. Actually, sorry, I lost all the animation. I don't know why, okay?
Say what?
The hint is you can see that this one must have the animation. Okay. Animation. Okay.
Inside also, yeah.
You see this? I want to search for successor of 11. 20 will be my successor. I want to search for the successor of 32. 41 is my successor. Any common property of this 20 and 41? Sorry? Speak louder, please. Yeah, both wonders. But then, why not 41 in this case? Why this one is not 41? Yeah, so the lowest one, right? So you find the lowest one, but actually the lowest one just now, when you follow the search, that go left. You have a lot of parents, right? You have a lot of lower parents, right? Okay, so you actually find the lowest parents that go left. That is your successor, okay? So the all in one is you follow the search to find the node for X, and if the node has a right child, you return the max of the right child, okay? And otherwise, you follow the search path just now and actually find the one that go left, which is the lowest. Because there may be a lot of people go left to find you, but the one who go left is actually your successor. Okay? So for example, 32, I come back this I want to find a successor of 32, and my parent is 29. That's not my successor. 20 is not my successor because 20 go right to find me, but actually 41 is the one who go left to find me. Okay, you trace it. But also in this tracing, until you trace back to the root, there will be some more people go left to find you, but you find the lowest one to find you. Okay. Yeah. So it also works for the keys not in the tree. Let's say I want to find the successor of 33. You actually will end up with 32 and you still use the same method to find the successor. Okay. Yeah. So at the end of the day, what is the complexity of finding successor? It also depends on the height of the tree. Okay. If the tree is deep, you have a long time. Okay. But if it's not, then it's not. Okay. So that's all for today. Let's answer some question on the Zoom or any question here. Okay. Actually, if you use Zoom, you have more questions. Okay, let's see. The first question, what if the left child is null? Then the parent is the successor. What was the question about? Yeah. I think for this question, it answered in the last way, okay? This one, okay? The last slide, which means this one, okay? You may stop, for example, let's say if I want to search for the successor of 20 in this node, I actually can stop here. And 20 has no left child, and you start here. But 20 can still have some children, but this case, 20 have a right subtree. And that's why you follow this rule. If the node has a right child, return the max of its right subtree. Okay, that answers this question. And if this 20 have no left node and no right node, then you follow this rule. Follow the search path to find the last parent that go left, and in this case is 41. Okay. Question: what if look for 100? Oh, okay, good. I think it's something I didn't talk about. What if you want to find a successor that does not exist in the tree? Okay, I think this is what Justin asking. Okay, that is how you need to handle it. Is actually you need to go to the error handling. Okay, if you want to find the successor, which is actually more, for example, this one, right? I think the question is exactly this one. If I want to search for 100, actually it's an error message. Okay, you need to search it, 99. But then you trace all the way back to the roots. No people go left to find you. If no people go left to find you, that means there's no successor. Then you actually have to do some error handling. Okay, it's the same thing. What if I give you an array to sort? Let's say merge sort, but you actually give me an empty array. Okay, those are error handling parts. in the end of this lecture, if we have time, we actually talk about the exception throwing, okay? So that means there's some abnormal thing you're going on, which how do you handle it? Okay, but this is an error you need to handle, okay? But the answer for that is you don't have a successor. There's a chance that if you want to do a query, you don't have a successor. It's just very simple. What is the flight after 11:59 p.m.? Then you may not have a flight after that. Then you may simply answer that there's no flight after that, okay? Or you may need to find out, oh, the flight after that is tomorrow or whatever, you still keep to it, okay? So it's a good question. Any more questions on the Zoom? Is it better if we have pre-calculated min and max? I think there's a good thing, okay? But if you have a pre-calculated min and max, you just need a constant time to maintain the min and max every time. You can actually do that. But that increases a bit of the computation complexity, okay? The advantage for that is you save the time, you save the log n time to search if what you need to search for is less than the min or more than the max. Let's say it even exists. I know the mean of my tree is 20, but I'm trying to search for 14. If I have an entry for that, I can immediately tell you in constant time, I don't have that in my tree, okay? But that means that is actually another level. Probably you learn it in your software engineering. That means whatever code to modify your tree and this and that, you need to update that min and max. So are you sure that when you implement a new function, I actually will go and update that? Okay, so that is just an extra one. But usually, for example, for this, you can actually go, what you're asking is a design issue, okay? So if you go back to this, this ADT, okay? What are the functions you need to maintain the min and max inside here? Insert, right? But wait, how about delete? Delete, if you need to delete the min and max, you need to look for your next min and max to update, okay? I don't mean it's a bad idea, but you need to do all this maintenance for the min and max, which is a good thing, okay? It's a good thought. Some people actually really do that. It's a good thought, okay? Is it possible to delete a number from the tree? Yes, okay? We'll talk about it next time. That together with our tree maintenance, okay? But you can, and maybe I can leave it a whole now. You can insert something, but how do you delete a node? Okay? If the node is a leaf, it's very simple. But what if your node is not a leaf? You think about how to maintain the pointer and rearrange the tree to make it a tree, okay? So sorry that for Justin, I will actually leave this question for next lecture. Okay, any more questions? Good questions, okay? So what we take is, this lecture is quite simple. We just describe all the trees operations. But at the end of the day, when we come to time complexity analysis, we need to maintain the tree heights, okay? So next lecture will be a lot of things talking about how do we actually maintain the tree heights for the next lecture, okay? So stay tuned for next lecture, and that's it for today. Oh, sorry. How do you traverse up the tree to find a successor? Okay, good. That is an implementation issue, okay? But of course, first, you can actually try to use some stack and flag. But that's one thing I actually didn't talk about. Actually, we can implement the parent pointer. Usually, actually, there's a norm. Because of simplicity of explaining tree, I missed that out. But usually, people actually also implement a parent pointer. So for every node, you actually know who are your parents. So it's almost like converting a single linked list to a double linked list. So you can actually go every direction, okay? So usually people actually implement the parent pointer to make everything simpler. Okay? But you can get around with that. If you implement it correctly or get some flag or something, then you actually can implement the whole algorithm without the parent pointer. Okay? But the simple getaway or the norm people do is get a parent pointer. Okay, good question. Colin and Justin and all these. If there is a need for new parents, parent pointer, not new parents. Okay, if there's a need for new parent, I don't know. Are you asking a real life situation? No, I'm just kidding. Okay, I don't know what does it mean by new parent. Okay, does parent pointer cause runtime to increase? In constant time, I would say. Yeah. The parent pointer will help. Actually, a lot of time it will help. Yeah, it will make things a bit simpler, but also make things a bit more complicated when you need to maintain everything. Okay, and you have to choose whether you want to use a parent pointer and you don't want. It depends on situation. Okay, that actually comes with later your labs assignment. Okay, the later lab assignment is one. You can do the whole assignment without the parent pointers, but maybe with the parent pointers is another level. Okay, so you just wait for the next assignment, the assignment 3. Any more questions? 3, 2, 1. Okay, thank you for everyone, and that's the end of our Zoom section and everything. I hope you okay with the Zoom section. Yeah, thank you. Yeah, come, it's ending. Yeah. Zoom. Zoom, yeah. It's pretty good. I think it turns out really good. Yeah. Yeah. In fact, people ask more questions in Zoom.
Really?
Because they type, they don't need to like raise hand. So, but they ask questions also. Yeah. Yeah. Zoom is more like more brave to ask questions in Zoom. I think. Yeah. Please log it out. I actually not using it.
Get distracted.
Yeah.
Right. So okay, maybe you show me since you're here.
Okay.
How do you?
You want to log in first?
Start off the. Not using it today, but I'll find out.
So log in first.
You got the contact or not?
Sorry.
You got the contact or not?
Before.
Have they written their names or not?
Oh no. Do I need to?
You're supposed to.
Oh, I'm supposed to.
Yeah, contact tracing. Remember.
Oh, too bad.
Yeah. But anybody who come for your class need to take that.
Oh, I did that for tutorial, but I forgot to do that. But this one I can remember. This is a Korean guy. I remember him.
If you remember, okay, just go back and write it.
The normal procedure is actually quite simple. For every computer, you may need to install for the first time.
Okay.
Okay.